You're driving over a massive bridge, right? And you just have to wonder, how? How is this gigantic web of steel and concrete weighing millions of tons not just plunging into the water below? Well, you've come to the right place. We're about to dive into the surprisingly simple physics that keeps these incredible structures standing.
So yeah, that's the big question we're going to tackle in this explainer. And spoiler alert, it's not magic. It's some seriously cool physics. By the end of this, you'll never look at a bridge the same way again. You'll see them as these amazing feats of engineering, constantly fighting a hidden battle with gravity.
You might think there's some super complicated secret, but it all boils down to just two things. Yep, two. Every single bridge, from a simple log over a stream all the way to the Golden Gate, is just a masterclass in handling two basic invisible forces. And here they are, compression and tension. Okay, seriously, try this with me right now. Press your palms together. Hard. Feel that squeezing? That's compression. Now picture stretching a rubber band. That pulling feeling? That's tension. That's it. That's the whole game. Every bridge is just designed to handle that push and that pull. All right, let's talk compression first. It's the pushing force, always trying to squash a material. This is exactly why you see so much stone and concrete in bridges. Those materials are absolute champs under compression. They just don't buckle when they're squeezed. And on the flip side, you've got tension, the pulling force. It's all about stretching something apart. Think steel cables. They have incredible tensile strength, which basically means you can pull on them like crazy and they won't snap. You got to get this fundamental push and pull, because it's the key to, well, everything we're about to talk about. Okay, so now that we've got the theory down, let's see how this stuff works in the real world. We're going to start with the most basic design out there, the beam bridge. I guarantee you've crossed thousands of these, and probably never gave them a second thought. And yeah, its design is pretty much exactly what it sounds like. You've got a horizontal beam, that's the deck you drive on, supported at each end by piers. Super simple, super effective, and a perfect way to see our two forces go to work. So how do the forces work here? Well, when a car drives over it, its weight pushes down, right? And that makes the beam bend, just a tiny little bit. Now, the top surface of that beam gets squeezed together. Boom, that's compression. But at the same time, the bottom surface gets stretched apart, and there's your tension. The piers are just there to push up and support the whole thing. And that's also its biggest weakness. The beam itself has to deal with both forces at once, which is why you just can't build them for really long distances. They just snap. So, how do you build longer bridges? Well, you have to get a lot smarter with how you handle those forces. And that brings us to the arch bridge, a design that is just brilliant. It actually turns the bridge's own weight into a source of strength. I mean, just look at that classic, elegant curve. See, unlike the simple beam bridge, the arch doesn't just try to muscle through gravity head-on. No, it's way smarter. It redirects it. The key parts you gotta know are the arch itself, obviously, and these massive solid supports on either end. Those are called abutments. The real genius of the arch is its shape. When weight pushes down from above, that curve doesn't just bend. It channels that force outwards and downwards, all along its length. What that means is the entire arch is under compression, that squeezing force it's so good at handling. And those abutments, their whole job is to push back and keep the ends of the arch from spreading out. It's just a beautiful, incredibly efficient way to deal with a massive load. Okay, but what if you need to go really big, like miles of open water big? For that, you need the undisputed champion of long-distance bridges, the suspension bridge. I mean, this is where engineering really becomes art. It's all about mastering the force of tension on a totally epic scale. Okay, looking at this, you can see it's a way more complex system, right? You've got these huge, tall towers. You've got the massive main cables that are draped between them. And then you have all these smaller vertical cables. Those are called suspenders. And they're what actually hold up the roadway or the deck. Every single one of these parts has a very specific job to do. Okay, let's follow the journey of the load. The weight of the cars on the deck is literally hanging from those vertical suspender cables. So those are in a constant state of tension. The suspenders then transfer all that weight up to the gigantic main cables. And those are under incredible tension. Now those main cables pull on the towers, putting the towers under compression. They're being squeezed. And finally, the cables are tied down into these gigantic concrete blocks called anchorages, deep in the ground. The load is literally hung from the cables and then safely channeled right into the earth. It's amazing. So there you have it. The beam, the arch, and the suspension bridge. 3 totally different designs. And as you've probably figured out by now, engineers don't just pick one out of a hat. Choosing the right bridge is always about choosing the right tool for the job. And it really breaks down pretty simply like this. For your short, everyday crossings, like a highway overpass, the beam bridge is cheap and perfect. For those medium spans, where you've got solid ground on both sides, like a deep valley, the arch bridge is an amazing choice. But when you need to cross miles and miles of open water, well, the suspension bridge, with its absolute mastery of tension, is pretty much the only design that can get it done. And that's really the beautiful thing to take away from all this. No matter how complicated or different they look on the outside, every single bridge is just a brilliant answer to the exact same simple question. What's the best way to manage tension and compression right here in this specific spot? So next time you're driving across a bridge, I want you to take just a second, look at its shape. Can you tell if it's a beam, an arch, or a suspension bridge? And more importantly, can you try to see those invisible forces at work? The constant push of compression, the relentless pull of tension, all working together in this perfect, hidden balance to hold you safely up. What do you see now that you couldn't see before?